Okay, so come back. So attendance is almost half, which is good. But then it will be manageable class, right? Otherwise, 300 is very large. But anyway, so now, so before starting the next lecture, so I think that in the last lecture or the first lecture, I gave you a kind of overview, a bit of historical thing, how things started. And now what I am going to do, I'll talk about codecs first, So what is, so in terms of this picture here, so basically all these 6 steps are important and we need to really understand each one in detail. So a lot of work has been done on codec, which is basically encoding decoding method, how to encode and how to decode. And there are methods which are very good in terms of capacity, information density, so they are very good. So we look into those kind of things, little bit of mathematical things, but more engineering flavor, so that you really see how things are happening. And okay, then we'll talk about synthesis, and there are many techniques. Basically, there are 3 main techniques, and those things we are going to look at later on, how the synthesis of the DNA molecule happens, and basically what is the chemistry behind it, and what kind of technology is right now available to do that. Storage and retrieval are kind of, again, how do you store? You can store just like a test tube. You can also store data on a glass plate or whatever. There are different ways people are thinking, and depending upon the kind of application that you want to do. And obviously retrieval. So this is kind of, it's a choice depending upon the application. Sequencing is all about reading. So again, there are different things, and sequencing, because of the Human Genome Project, a lot of progress has been done on it. Sequencing means reading the DNA, right? You want to read the genome of anyone. By the way, as an exercise, have you seen DNA? Any one of you? You can see at your hostel also, you can actually, extract DNA from any living thing, maybe strawberry or banana or whatever. You can look at the Google. There are ways how to do it. What you require is sprit, the alcohol, rubbing alcohol basically, and soap, and maybe a test tube or whatever, or maybe any koi bhi button le lo, right? So then what you do, there is a procedure to extract it at home. So if you search on Google how to extract DNA, you can actually see physically, then you will get some feeling. So this is an easy exercise for you. I would say it's a tea time problem. So you can actually extract DNA. If you want, you can extract your own DNA also, but I mean, that's okay. I mean, you can try with fruits, right? So this is something very easy thing to do. Okay, so that's about reading. So first, I'm going to focus on codec. Codec means encoding decoding procedure combined, right? And there are different algorithms. So this is mainly algorithms, right? Different kind of algorithms. Something is performing better, something is not performing very better, but there are different aspects in which one can use depending upon the kind of application that you are looking at. Okay, so I'm going to start with codec, and to understand codec, because the job of the codec is to correct as many errors as possible, right? When you want to correct errors, when you are storing data, errors are bound to happen, right? Reading errors will happen, writing errors will happen, and storage errors will happen. And actually, when we store data, most common error is deletion. Bunch of fragment will be deleted. Okay, and so how to repair it? So deletion error correcting codes are required. Different kind of things. Which is kind of a little bit different coding theory or error correcting codes. So I'm sure you have not done a course on coding theory, right? This course, although I think some of you might have done it, right? I mean, it's available on my YouTube channel, so if you want, you can look at it. I'm not going to cover the entire course because then I'm teaching that, right? But I'll take some important things so that you understand the key concept that is sufficient for you to jump into the codecs for the DNA storage, right? So that's how I'm going to start. Any questions? So basically, we are going to study these 6 parts. The whole course is divided into these 6 parts, and for each one, we are going into looking at the details. Okay. So first thing is about codec. Now, when we want to go for the codec, I need to look at error correcting codes. So, very brief idea I will give you about error correcting codes and some elementary ideas. So that today I'm going to discuss only elementary ideas so that you understand how error correction works in our actual storage. I mean, whenever you are storing data on hard disk, your phone, or any other media, you require error correcting codes. Without it, you cannot do anything. It's the most beautiful algorithmic construct which is sitting behind every application, right? Whether it is your software that is handling data, or actually data storage or data communication from one device to other device, or from satellite in your internet, without error correcting codes, those are the beautiful algorithms which are sitting and actually providing you error-free communication and data storage, right? So that's why when we are looking at this technology of DNA storage, again we require error correcting codes. So how they started? Although the binary vectors were known in India long back from the work of Panini, but I would look at this picture. This is Bell Labs, New Jersey, and here was something around 1946 or 47, I would say, when Richard W. Hamming, he was working on Manhattan Project. So he used to solve a lot of differential equations using those days computers. Okay, so this is Model 5 Bell Laboratories General Purpose Relay Calculator. Similarly, there was sorry, this is Model 1. He was working on Model 5, such kind of machine, and he used to give instructions to the machine on a weekend, and every Monday whenever he comes, many times it happens that the machine has stopped because of an error, and he was very frustrated. He said that can we design machines which can correct automatically the errors? So at those times in computers there was not error control of that kind, right? There was no error control. So what happened? So he asked this question: when a machine can detect an error, why it cannot correct it? And this resulted in Hamming code. I'm going to give you a brief idea about Hamming code probably towards the end of the lecture. So how it works? Beautiful idea. So Hamming code can correct single bit flip. If 0 is flipped to 1 or 1 is flipped to 0, it can correct it. Okay, nicely. And they are kind of mathematically, they are beautiful codes in terms what is known as perfect codes. So what do you mean by perfect codes? If we draw spheres of radius 3 along each code word, they cover the whole space. Okay, so this is something beautiful property that these codes have. So okay, so these codes. In fact, the dual of these codes were known in statistical design. Something around 1945. See, so the birth of new ideas is happening at the same time. 1945, something happened in design, and again 1947, those things were rediscovered in another application. This is the beauty of mathematics, right? Things are connected anyway. So at the same time, Cloud Shannon, Cloud Shannon was also at Bell Labs in 1948. He wrote a beautiful paper, Mathematical Theory of Communication. So if you really want to understand the idea, I mean, people call him father of information technology. Basically, he gave the idea how much, So basically, if you are transmitting bits, what is the ultimate capacity through which you can transmit the bits? Or if you want to store data, so or you want to compress data, how much you can compress data, the digital data, right? And he gave this probabilistic paper. You can read this paper, Mathematical Theory of Communication. It's a very beautiful paper. So this gave birth of information theory, right? So information theory answers to fundamental questions, or rather sets bounds on information storage, how much information we can store in a given place, and information communication. So basically, how much we can communicate. Okay, these are the two very basic bounds. So basically, information theory is a branch which study how much. Okay, it's kind of gives you the bound, how much you can do, right? How much you can communicate, how much you can store. Very basic questions, and those are mathematical things. But in fact, he used the Hamming code in that paper, that example, because that's what is discovered anyway in 47. Actually, that paper was published by Hamming in 1948 because he filed a patent also on this, right? So it took some time before publicly it was available. So But before that, as an example in this, in his work, Shannon work, that that example was given. This is something really beautiful. So if you really want to understand information theory, I would suggest read this beautiful paper, Mathematical Theory of Communication. If you really want to look at almost 50 years development, because from 1948 to 1998, you can look at another paper in 1998, which is kind of a survey paper, which appeared in IEEE Transactions on Information Theory about what kind of things are there, different kind of channels. Because whatever you're doing for simple bits, channels could be different. Okay, channel could be different means when we are storing data, the media could be different. So here we are going to talk about DNA, but it could be optical storage, or it could be some other kind of device where you are storing the data, or communication of any kind of thing, right? So different kind of communication devices and different kind of storage devices give rise to different kind of channels, and those channels requires error correcting codes. Okay, so the birth of data compression. So Huffman codes that you see is actually an example of data compression technique, right? Huffman codes you saw in your discrete math class, right? That was the binary Huffman coding. So you remember where there we look at certain letters and look at the frequency, and according to that we construct the tree to do those things. So the question is how much you can compress the digital information. So answer is entropy. I'm not going to give you any more details here, but yes, that can be in a separate course on information theory. Okay. Now, coding theory, which is again a sister question because error correcting codes or coding theory, there are three types. Source coding means data compression. So Huffman coding is one example. Data compression, there are many techniques. I think you might have used all this. You must have used ggip, right? Have you used ggip or zip? All compression algorithms use some sort of beautiful algorithms use some sort of code, compression codes, right? So that is source coding. Channel coding. So there is a channel, there is a message, sender will encode the message, send across the channel, noise will be there, noise is there, will be there anyway in any kind of communication. Receiver will receive it, then it will use the decoder or the codec, and then you get the actual information, right? And so one area is source coding, one area is channel coding, and third area is joint source in channel coding. So there are techniques where you are also using compression and the other channel thing, right? Both the things are combined. So these three areas will have different algorithms to encode and decode the data, right? So this is something very, very important, depending on which kind of things we are using. So now, in terms of DNA storage, people have used, so since last 50, 60 years, 70 years, we know what kind of algorithms are good. So what people are doing, take that algorithm and see if you can get something good. In the case of DNA storage, sometimes they are successful, and and that's a beautiful paper, right? Ultimately, you can design the whole thing. So this is a basic idea about coding theory. Now, how to construct codes? So how do you construct these algorithms? So answer is some combinatorial mathematics, algebra, or linear algebra course you might have done, right? Algebra course is happening this semester, right? But that is a very, very important thing to do something. And of course, depending on the application, So algebra is very beautiful, right? An ounce of algebra is worth of a ton of verbal arguments, right? If people are doing verbal arguments, just an ounce of algebra is sufficient to stop. Algebra is so beautiful when a protein interacts with another protein or with another small molecule, they follow Clifford algebra. Same Clifford algebra is useful in wireless communication. So all beautiful things are connected, right? Application could be anything, but there is a strong mathematics behind it, right? So the ultimate goal is, so when I'm speaking to you, suppose I'm talking to you and you are unable to understand. So what you will say? So that means if something is, I'm telling you something you're not able to understand, so that means there is some gap, right? Some sort of error has happened, right? So how will you correct that error? You will say that please repeat. So repetition is a crude form of error correction. Okay, just repeat the information certain number of times. So just like that, as I mentioned to you earlier, in the cloud storage, Gmail used to replicate each packet 35 times. Okay, across the nodes so that you can reconstruct the file. So if there is error, so if there is a in fact now there are techniques after 2007 or so, what is known as regenerating codes for the cloud computing. In the case of regenerating codes, what is happening? You take your data file, divide into chunks, encode the chunks, and throw into the cloud of n nodes. Now, if you want to reconstruct the file, contact any k nodes in the system out of n nodes, and you will be able to reconstruct the file. So beautiful algorithm is sitting there, which will reconstruct the file just contacting any k nodes out of n nodes. Okay. Second, if a node fails, then node can be repaired by contacting any d nodes in the system to reconstruct that data. Now the reconstruction is of two kinds. First, whatever was lost there, replace exact data that was lost there. Or second is a functional repair. Functional repair means, the property to remains true, that you want to reconstruct the data, you just contact any k nodes. It doesn't matter what is now the new data set in this node which was failed. So this kind of techniques are available right now in what is known as regenerating codes. Very useful for cloud computing. People who are looking at cloud computing or distributed storage, these kind of algorithms are available right now. And I think all these big companies, for example, Microsoft Avalanche file system, I don't know whether you heard about it. Microsoft Avalanche file system is based on this technique only. Facebook started moving most of its data in this technique because this is useful. See, so in this regenerating codes, what happens? You reconstruct the data. So basically, there is a trade-off. If data is failed, so you want to minimize amount of data is stored on each node, right? You want to minimize. You don't want to store too much. Also, you want that the repair bandwidth should be small, right? When you're repairing, you're downloading data from somewhere because it is replicated somewhere else, right? So you have to minimize the repair bandwidth. So those kind of constraints are there. And also you want your algorithms to be scalable, right? So today you have 100 nodes, tomorrow you have 1,000 nodes or million nodes. Algorithms should work in the same manner, right? So the different kind of parameters, optimization parameters are required. So the regenerating codes is in one such beautiful idea for cloud computing, right? So which is again using coding theory. Now, so the target is we use redundancy in a clever way. Let me show you example. So now I'm going to give you some very basic example of classical error correction techniques that are quite common. So look at this picture here. We have, suppose we have two things I want to say, yes or no, right? So yes, I encode 1 and no, I encode 0. Okay? Yes, I encode 1 and no, I encode 0. If I send 1 across the channel and suppose bit is flipped, 1 becomes 0, right? Then it will be difficult for us to tell how to correct the error, right? I will not be able to correct, right? If 1 becomes 0 or 0 if I send and it becomes 1, if 0 becomes 0, it's fine. But it may happen it may flip because of the error. So I am assuming that there is a flip errors that is happening quite common, right? Okay. So what I do, I repeat. Remember, repetition is very crude form of error correction. So I repeat 1 as 1, 1, 1 and 0 as 0, 0, 0. Okay. So now I am sending, if I have to send yes, I will send 1, 1, 1. If I have to say no, I will send 0, 0, 0. Now what happens? Suppose I sent yes, okay. So yes is 1, 1, 1. I have sent. And suppose errors happen, one bit is flipped. Suppose one bit is flipped. And you receive, say, 1, 1, 0. Last bit is flipped. You can see that, right? Now I want to correct this error. How should I correct this error? I know that all the messages, either this is sent or this is sent, right? So I just collect them and I call it as a code. This is our error correcting code. I call it as a code. I received 1, 1, 0. Now I compare 1, 1, 0 receive vector, this and this. And I ask this question, 1, 1, 0 is close to 0, 0, 0 or 1, 1, 1? Now this closeness, you can guess in terms of what is known as distance. Number of places they differ. This and this differ in how many places? 2. And this differ in how many places? 1. So which one is closest? This one, right? So once I received 110, I say that 111 was sent. So this is known as, nearest neighborhood decoding, or, using distance idea, I'm just comparing, right? Whatever is received, I just compare with the everything, right? Suppose, if you send 111 and suppose receipt vector is 101, again the same technique will work, right? So either bit is flipped. If I send 111, either bit is flipped. Only single bit is flipped. I will be able to correct the errors. Correct? Now what about, suppose there are 2 bits flipped. I sent 111 and suppose 001 is received. So 2 bits are flipped. Can I correct now? So what I need to do as an engineer, think about it. What we should do now? I given you a construct which is correcting single bit flip. Now I ask you, same problem is there. What should I do so that I can correct more errors? So suppose now I want to correct 2 errors. So how many times should I replicate data? 5 times, right? So basically, this 1 will be 1, 1, 1, 1, 1 5 times, and 0 will be 1, 0, 0, 0, 0, 0 5 times. Then you will be able to correct 2 errors with the same method, right? So if I have to correct 3 errors, how many times I need to repeat? 7 times. Now you are getting an idea. So essentially, this whole thing is governed by what is known as distance. With this distance was defined by Hamming himself, and this distance is known as the Hamming distance. So number of places they differ actually, right? So if the minimum Hamming distance, so suppose C is our code, you compute the distance among all the pairs, right? So what is the distance here? 3. 3 is the minimum distance, right? Among all the code words, all the vectors. So if distance is D, you can correct D minus 1 by 2 errors. This is a theorem. If distance is D, you can correct D minus 1 by 2 errors. So for example, here, if distance is 3, so 3 minus 1 by 2 is how much? 1, right? So you can correct single error. If distance is 5, so 5 minus 1 by 2, you can correct 2 errors, right? So there is a mathematical nice technique. If distance is D, we can correct D minus 1 by 2 errors. And we can detect D minus 1 errors. So there is a result actually, right? So this is something. Got the idea? So basically, this Hamming distance between x comma y is number of places that differ, right? So if distance is D, it can detect D minus 1 errors and correct D minus 1 by 2 errors. So as a t time problem, maybe you can prove this fact, right? If distance is, of course, this is available in the detailed lectures. If you want, you can look at it. But just, casually pick a cup of coffee and tell me if you can do this, right? If the distance is D, you can correct D minus 1 by 2 errors, right? If you can prove it, beautiful proof, actually, by the way. So that will be an interesting thing to do. Okay. So basically, so what I gave you the idea about, this was binary coder. To remember the first class in discrete math, you remember first class or second class maybe? We have done a lot of business on finite fields. Remember? Finite fields. Must have enjoyed it also. Those integer modulo n, right? Integer modulo n is a field if and only if n is a prime number. Remember? And also that field with 4 number of elements, 0, 1, alpha, alpha square, those kind of things. Those are very, very important thing, because these data packets are nothing but these elements of the finite field, right? So they are very, very important things. So, right, that's why I gave you flavor at that time, early stage, so that you can really understand. So now, assuming that you know this, or should I cover some of that stuff again? Maybe I can just write it down. I hope that you can recall some of this stuff. So remember, integer modulo n is a field if and only if n is a prime number. Right? This is one thing. Integer modulo n, remember, so Z2 is a field, Z3 is a field, Z4 is not a field, Z5 is a field, Z6 not a field, Z7 is a field, Z8 is not a field. So the question is, so we have n is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 is a field, 3 is a field, 4 is not a field, 5 is a field, 6 is not a field, 7 is a field, 8 is not a field, right? 9 is not a 9 is a field or not? 9 is not a field, 10 is not a field. But I have given you an idea how to construct field with 4 number of elements. If you remember, Galois field with 4 number of elements consisting of all elements of the form A plus alpha B, such that A and B belongs to Z2 and alpha square plus alpha plus 1 is equal to 0. Remember? So this is nothing but 0, 1, alpha, alpha square. Right? You can also say that 0, 0. 0, 0, 0, 1, 1, 0, 1, 1. Bit representation. We have 3 representations of the field, remember? Another one is 0, 1, alpha, and 1 plus alpha. 3 representations, if you remember, recall. This is the power of alpha representation of the field with 4 number of elements. Polynomial representation. This is polynomial representation, and this is the bit representation, right? Just recalling your. No, it has been long. 2019 or 2020? 2019, yeah. So this is very, very important, right? So this field with 4 number of elements, so we can construct field with any prime power. Remember? So in general, we can construct field with prime power. I call it as Galois field with Q number of elements, where Q is a prime power, right? In general. So it will be power of alpha. You can represent everything like that. Yeah. Why we so because we are talking about data which is discrete, right? So that's why we require this discrete structure, right? The finite fields. Now these finite fields are because whenever we are doing all these packet operations, this and that, we are doing with elements with finite fields, right? So you might have seen real or complex normally, the fields real or complex. But, so, and you might have seen in your linear algebra course, right? You might have seen vector spaces. You have an idea of vector spaces? भूल गए? I think वेक्टर स्पेस तुम्हारे डेटा साइंस के लिए भी बहुत जरूरी है, मशीन लर्निंग के लिए बहुत जरूरी है, राइट? इट्स वेरी इंपॉर्टेंट. Linear algebra is very, very important actually. But the thing is that because it was on real or complex, you may have no feeling about it, right? You should be able to touch the vector space. I can show you how to touch the vector space when you shift your everything to finite field business, right? So let me show you a few things. मेरे को तो दिखता भी नहीं है इसमें. Okay, so what I am going to do now, look at this. Z2 is a field, remember? 0, 1 element, it is modulo 2. So I can look at Z2 raised to power n, which is all vectors of the form x1, x2, xn, such that xi belongs to Z2. So you can have analogy with real numbers and dimensional vector space, which you might have seen here in your linear algebra course. So I am worrying about that kind of space. Right? It's the same thing. This you might have seen earlier. Or c raised to power n. Cross c n times, right? So these codes, the code which I gave you the first example, c is equal to 000, comma 111, it is coming from a vector space only, right? And what is the length? 3. So z to 3 is how many elements are there? So I can take a specific example for n is equal to 3. They should give you z to 3, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. These are all 8 elements. See now here you can touch. Else में तो touch नहीं कर पा रहे हो ना? You know how many of them are there. What is, I mean the total size of the space. In case of Rn, how many elements are there? R is for n. How many vectors are there? Infinite, right? So here, but everything is finite, so you can feel touch. There, if I asked you to abstract a subspace, you just write a formula. Here, I can show you the subspace. So that vector 0, 0, 0 and 1, 1, 1 is a subspace here of dimension 1. Right? So if we take C is equal to, this is a subspace. Z to 3, what is the dimension? 3, right? Because there are 3 linearly independent vectors which can generate the whole space. What are those vectors? 0, 0, 1, 0, 1, 0, 1, 0, 0. I mean, there are many others possible, but these 3 are sufficient because these 3 vectors are linearly independent. Remember? These 3 vectors forms a basis. These 3 vectors are linearly independent, means lambda 1 times this plus lambda 2 times this plus lambda 3 times this is equal to 0, means all scalars are 0. Right? So these 3 vectors are linearly independent. If I take 2 vectors, if I ask this question whether 2 vectors are linearly independent, means first vector should not be lambda times other vector. Right? So then they are linearly independent. Right? Here, when there are 3 vectors, so I am taking linear combination. Lambda 1 times first vector plus lambda 2 times second vector plus lambda 3 times third vector is equal to 0 should give you all scalars 0. So these 3 vectors are linearly independent. I can maybe mark it here. This, and this, right? These 3 vectors are linearly independent. Second, they span the whole space. If I take any coordinate, any vector in the whole space, z to 3, it is linear combination of these 3 vectors only. Right? If I take, say, 1, 1, 0. So 1, 1, 0 is sum of this and this, right? Take any vectors, right? It will be linear combination of all these 3 vectors, right? So they have unique representation, right? Each vector you can generate using these 3 independent vectors. So these 3 independent vectors form say what is known as basis. ये पढ़ा होगा vector space में, right? Basis. So dimension of the whole space is 3 here, right? Because this is a basis. Now, what else? I can ask many questions. So if you remember n-dimensional space, how many one-dimensional subspaces are there in, say, Rn? How many one-dimensional subspaces are there? All lines passing through origin will be one-dimensional subspace. Remember, in R raised to power n, all lines passing through origin will be one-dimensional subspace. Okay. But what about here? How many one-dimensional subspaces will be there? Any idea? ये सब लीनियर अलजेब्रा कोर्स में पढ़ा होगा. ये कंपलसरी कोर्स है ना? It's okay. हर एक ने किया है. So one-dimensional subspaces कितने होंगे? One-dimensional means the basis should have only one vector. If I, okay, So basis is having only one vector. So because the dimension comes from the basis. Here the dimension is 3 because basis has 3 vectors, right? If I ask you one dimension vector, so basis has only one vector. So if I take 0 vector, can it be a basis? No, because lambda times 0 will be 0, right? So because this lambda is not coming up to 0, right? So basically what I'm saying that this is dependent. In that case, I take any non-zero vector that will form a one-dimensional space. Any non-zero vector out of this, and how many of them are there? 7. So there are total 7 subspaces of dimension 1. If I take vectors generated by 0, 0, 1, so the space generated by 0, 0, 1, the total two vectors will be 0, 0, 0 and 0, 0, 1. Right? Basically, I am saying that if basis is generated by just one vector x, x is not equal to 0, and it belongs to Z to 3. So suppose I take 1, 1, 0, space generated by this, C is this, right? So this is nothing but lambda times 1, 1, 0, where lambda belongs to Z2. This means 0, 0, 0 and 1, 1, 0, two vectors only, right? One-dimensional subspace. If I take some other vector, there also, because one dimension means lambda times, so there is only one scalar right here. Two dimension means, you remember, two scalars are involved in generating the vectors. Three dimension means three scalars are involved, lambda 1, lambda 2, lambda 3, right? So now this is one dimension. To look at other ones. So one space will be 0, 0, 0, 0, 0, 1. One space will be 0, 0, 0, 0, 1, 0. Another space will be 0, 0, 0, 1, 0, 0. Another space will be 0, 0, 0, 1, 1, 0. Another space will be 0, 0, 0, 1, 0, 1. Another space will be 0, 0, 0, 0, 1, 1 and 0, 0, 0, 1, 1, 1. 7 one-dimensional subspace. This subspace is of dimension 0. If you take this vector, so this is a singleton 0, right? So this is the lowest one of dimension 0. Dimension 1, dimension 7, there are, so dimension 1, there are 7 vectors, so 7 spaces are there. So total 3-dimensional vector space, the full space is 3-dimensional because length is 3, right? So total 8 vectors are there. Out of using those 8 vectors, I can form 7 one-dimensional subspaces, right? And one 0-dimensional space, right, which is singleton 0, right? How many 2-dimensional subspaces? Because 2 is still less than 3, right? So 2 dimensions, you can take any 2 which are linearly independent. For example, these 2 will give you 2-dimensional space. How many vectors are there? What are the vectors in 2-dimensional space here? 0, 0, 0, 0, 0, 1, 0, 1, 0, and sum them, which is 0, 1, 1. All 4 will be 2-dimensional space, right? So you can take any 2 vectors which are linearly independent out of these 8 is space, right? 8 vectors. In fact, 0 you should avoid. So out of those 7, because if singleton 0 will be there, that will be dependent, right? So you need to avoid that. 7, you choose 7, choose 2, right? Which are linearly independent to make 2-dimensional subspace, right? 2-dimensional subspace will have 4 vectors. 1-dimensional subspace will have 2 vectors. 0-dimensional subspace will have 1 vector. Got it? So butterfly, dekhe na, butterfly. You can make butterfly here. How? Lower mein lagao 0-dimensional space, which is singleton 0, 0, 0. Upper mein lagao full space Z2 raised to power 3. All 8 vectors are there. Okay. So which is dimension 3, this is dimension 0. So dimension 0 के ऊपर आएंगे dimension 1 vectors. All those 7 vectors आ जाएंगे. Subspace आ जाएंगे, 7 subspaces आ जाएंगे. उसके ऊपर dimension 2 के subspaces आ जाएंगे. Dimension 3. तो ये उसका space, वो उसका ऐसे करके you can make a butterfly picture, right? कितना beautiful है, right? VLs में तो दिखता ही नहीं है. You can make butterflies here. Got it? Any question? Rn में क्या है? All, so Rn में one dimensional spaces are all lines passing through origin. There are infinitely many lines passing through origin. यहाँ पे तो finite है, I can count. There are only 7 in this case, right? Actually ये तुम्हारे linear algebra में ये सब examples नहीं दिए गए होंगे, but these are the ones which are real. बाकी तो real complex में real नहीं है, but anyway. But this is which you can touch actually and feel. These are the very important. ठीक है? So this is the. Now you see the code that we use for error correction is nothing but a subspace of this space, right? Now, what do you mean by subspace? I am calling subspace. What do you mean by subspace? Subspace means if I take two vectors, say u and v in this subspace, and I take the linear combination, say lambda times u plus v, that should also belongs to this subspace, right? Remember? So this linearity property is preserved, right? Right? This is the key thing, right? So if you remember subspace definition, no. So basically, this is obviously has to be subset of this whole space, and then this linearity property is preserved here. So basically, if I take two vectors, sum them, you are in the set itself, right? Okay. So this is the subspace idea, right? So I think a couple of things for tea time. First, you create lattice structures, right? So that you get a hand of it. So dimension 0 subspace, dimension 1 subspace. There are 7 of them. Dimension 2 कितने होंगे और dimension n के sorry n नहीं 3 right? So 4 layers, and you can make connections, right? That will be the butterfly for or lattice structure. We call it lattice structure of subspaces, right? Now, this was all about n is equal to 3. One may ask a general question: if there is an n-dimensional vector space over a finite field of, say, suppose we are looking at how many k-dimensional subspaces are possible. Total, in general, formula निकाल सकते हैं हम. There, we need to do some sort of argument. First vector can be chosen in how many ways? Obviously, you can see that here. First vector could be any non-zero vector. So that can be chosen in how many ways? 2 cube minus 1, right? 2 cube minus 1. 7 ways you can choose the first vector. One-dimensional subspaces in every vector, right? In case, when we want to construct two-dimensional subspace, so you have to take two vectors which are linearly independent, right? So how to construct that? So you have to build the argument. A bit non-trivial, but it's not very difficult. It will require you 2-3 more cup of coffees, but you will be able to construct, right? So that is there. But yeah, there is a formula, and the formula is in what is known as Gaussian binomial coefficient. You might have seen binomial coefficient, but there is a Gaussian binomial coefficient. So it is something like this. Gaussian binomial coefficient over Q. If the field is having Q number of elements, right? So this is all about some basics, right? So obviously you can find a formula for this, right? Now, Isha, right? Isha. So now she is working on one special kind of rings like rings. They are finding this kind of formula is still open. Nobody knows how many subspaces will be there, right? So that is something interesting problem. So I'm saying that depending upon which ring you look at, and if you try to construct the subspaces, sometimes it is difficult. We don't have a nice formula, which is a good thing. I mean, good thing or bad thing both. I mean, there's something to do, right? So anyway, that is something interesting. So in general, I can say, I can look at FQ. FQ is field with Q number of elements, right? And I can look at vector space FQN. All vectors of the form x1, xn, such that xi belongs to FQ. FQ means field with Q number of elements, right? Or GFQ, whatever. Some people write it like FQ. Some people write it as GFQ. Short form में FQ लिख देते हैं, right? So this is FQN. This is the vector space over the field FQ. So code is nothing but a subspace. A linear code is nothing but a subspace of SQN. A-dimensional subspace. Okay, so linear code, which is used for correcting errors, is nothing but mathematically a subspace of a vector space over a finite field. Got it? It's a subspace of a vector space over a finite field. Why we are calling this vector space? It's a collection of vectors satisfying those linearity property, right? Their linear combinations again in the set, right? Each vector space has a basis, right? So if the vector space is of dimension n, the basis has n vectors, right? All those vectors are linearly independent, number one. Number two, any vector in the space is linear combination of these n vectors, right? This is the summary. I gave you this example, but I think I'm just giving you, I have a theorem proof पढ़ाने नहीं आया हूँ, right? I'm just giving you importance, right? मूल तत्व, right? That is what is very, very important. These are the important things. ये दिमाग में example रहता है, then you can construct anything, right? बाकी तो theorem proof है ही book में, right? Got it? So this is the subspace. Let me. Time is over. 12:50 तक है ना? ये अभी नहीं करेंगे, तो नहीं तो फिर ज़्यादा हो जाएगा, ठीक है? So in the next class we continue, and then I will give you some more ideas about error correction, right? So I hope आज की चाय के लिए वो लेटेस्ट स्ट्रक्चर बनाना बटरफ्लाई, so you can do for dimension 2 का भी ले सकते हो, Z2 स्क्वायर, वो ज़्यादा आसान लेटिस पड़ेगी, राइट? Z2 स्क्वायर में 4 एलिमेंट्स हैं, वन डायमेंशन में कितने सब स्पेसेस होंगे? 3 ओनली, राइट? एंड देन यू कैन कंस्ट्रक्ट द लेटिस एंड 3 का ले सकते हो, राइट? So you understand the relationship, symbiotic relationship between different subspaces, and these subspaces are important. And from coding theory perspective, people ask how many subspaces. So I'll show you the decoding is difficult problem. When we do encoding, that is fine, that is easy. But decoding is a difficult problem, okay? Because we have to search, the subspace is quite large. Okay, so we have to search the subspace, right? So we'll talk about it more later on. Thank you. That's another layer on the top of it.